Okay, this lecture is going to cover reliability analysis. And basically, reliability analysis answers the question, how well do we know what we are doing? And this is the Terzaghi lecture that was given by John Christian back in 2004. And that's exactly what he titled his paper, Geotechnical Engineering Reliability, How Well Do We Know What We Are Doing? This paper is a really good introduction to reliability analysis. It could easily be an entire course, semester-long course, or maybe even a year, to really get into the details of reliability analysis, because there's a lot of calculations that have to happen to get it. So anyway, what we're talking about with reliability analysis is computing a probability of failure. A lot of the time when we do slope stability analysis, there's some kind of prescribed factor of safety that we have to meet, like 1.5, or maybe it's a little. Sometimes it's lower for seismic slope stability problem, 1.1. For foundation problem, it's often 3, and we never often question why is it that that's the appropriate factor of safety. We just have to meet it for regulatory reasons or something like that. So in reliability analysis, we don't do that. Instead, we quantify uncertainties in the capacity and the demand of the system that we're analyzing, and we design the capacity to provide an adequate probability of failure given the demands. So I wanted to motivate this by showing some things from John Christian's paper, and I'm going to go through some of these figures in just a minute, but there was an example in his paper that was actually originally done by Heinz and Van Marke of an embankment, and there was a roadway that was abandoned, and some researchers from MIT, here we go, we're starting to get into it, so on page 11 of 19 in the PDF file you'll find this. There was an embankment that had been abandoned, and some researchers from MIT decided that they were going to add fill on top of this embankment until it failed the clay soil that was underneath the embankment. And they held a workshop and gave detailed information to a group of 7 experts and asked them to estimate the amount of fill that would have to be added in order to fail the embankment, and to also give a range that corresponded to their 50% confidence interval, or those are called the interquartile ranges, right? So like I'm 50% sure the actual amount of fill that causes failure of the embankment will be between these two numbers and within this range. Okay, so let's take a look at the results. They did this load test, and what we're seeing here is that the squares correspond to each expert's mean prediction, like this is the average amount of fill that's going to have to be added, or the best guess of the amount of fill that will be added, and then the vertical bar is the interquartile range. We would expect, if the experts were good at predicting, that the squares would lie close to the actual amount, and that the actual amount of fill would lie within their 50% confidence interval as well. What we find instead is that the actual amount of fill added was 18.7 feet. Most of the experts predicted less. Some experts predicted more. And none of them predicted a 50 percentile range that encompassed the actual amount of fill that was added. It was in between there. So the experts were overconfident in their predictions, right? They didn't give big enough error bars on their results. If you average the 7 experts, it's 15.6 feet, which is actually not too bad. It's the average of the 7 is better than any single expert did on their own. Okay, now as part of this workshop, they also surveyed the audience. So this is an audience of people who would attend a workshop involving addition of fill to an embankment. This is not like random people. These are probably mostly geotechnical engineers, but without the benefit of having detailed site investigation data and soil strengths and things like that. They asked the audience to estimate the amount of fill that would have to be added, and this is the result of the 27 or so audience members. And what you'll find is that the audience did a lot better than the 7 experts. Just randomly polling the audience resulted in a better average, and also more of the 50th percentile confidence intervals encompassed that actual amount of fill that had to be added. So the reason I'm showing this is just to kind of pose the question, how well do we know what we're doing? All of us are going to be experts or are experts in our field, and people will pay us to do this analysis. It's important for us to kind of step back and think, how well do I know this? There's a lot of uncertainty in geotechnical engineering because we don't know the soil properties all that well. There's a lot of details of the geology that can be important for a problem, and we just don't know it. It's important to try and quantify that. So I'm going to change now over to drawboard, and there we go. Try and get rid of all that extra stuff. And we'll define a few terms here and just do a real basic sort of overview of reliability analysis. So I'm going to use some notation here where we have R is equal to resistance and Q is equal to load. And that resistance and load can be in whatever units are appropriate. In this case, I'm going to do an example problem where the load and resistance are in terms of stress. The load is a driving shear stress or a static shear stress, and the resistance is a drain shear strength. So we have an equilibrium shear stress and a shear strength that we're comparing. What we've been doing so far in slope stability is computing the factor of safety, which is the ratio resistance divided by load, right? So this would be undrained strength divided by equilibrium shear stress for a factor of safety. It turns out that that's not the quantity that we usually use in reliability analysis. Instead, we use the margin of safety, which is the difference between them. It's R minus Q. So the factor of safety is dimensionless. The margin of safety has the same units as R and Q. It's the difference of two quantities. And the reason why we do that is that generally R and Q are random variables. And if we take the difference of the random variables, the statistics of the margin of safety are a little easier to compute than if we take the ratio, and the statistics of the factor of safety get distorted. So if R and Q are, for example, normally distributed random variables, then M is also a normally distributed random variable, while F is not. So we would have to do a different distribution function for F. So for that reason, we generally favor M, and we're going to use margin of safety in the reliability analysis in this section. So let's say that R and Q are normally distributed random variables. We would need then to describe them by defining a mean and a standard deviation, right? The moments of the distribution function, 2 of them are required for a normal distribution function. So for example, we would have, this distribution function, probability distribution function for the resistance, and maybe this probability distribution function for the probability density function for the load. And the resistance, the mean value of the resistance, it better be bigger than the mean value of the load, right? So in this case, here we would have, this is the mean value, mu, q, and then the standard deviation, describes the spread. This would be sigma sub q. And then here we would have the mean value of the resistance and a little bigger standard deviation for resistance in this case. Doesn't have to be that way, right? Sometimes there's a lot more uncertainty on the loading than there is on the resistance. Earthquake loading is an example where there's really high uncertainty in earthquake ground motions and so forth. Okay, so we have now defined standard deviation of resistance and mean of resistance, and then mean and standard deviation of the load also. And technically up here, the factor of safety, if R and Q are random variables, we would need to compute the factor of safety as the mean of resistance divided by the mean of Q. So we have a new definition now that we're treating them as random variables. Mean of resistance over the mean value of load, right? All right, now an important aspect here is that sometimes the load and resistance are correlated. In fact, we'll do an example where the load and resistance are correlated. They're not always correlated. Okay, sometimes the load comes from an external source, like a building, putting pressure on a foundation, um, and we don't know for sure what the live load will be in the building, at some time that we're worried about failure. In that case, the load and resistance really are not correlated, right? The strength of the soil is not related to however much load happens to be on the building, or like for earthquake loading, the amount of inertia the building imposes on the ground, not really correlated with the strength of the soil necessarily. But for earth structures, the driving load comes from the unit weight of the soil, right? The heavier the soil is, the more shear stress it imposes. And in general, denser soil that's heavier is also stronger. So there is a correlation sometimes between load and resistance. So if we have two, again, we're assuming that R and Q are normally distributed random variables, right? So we're saying something about the shape of these distribution functions in addition to knowing the mean and standard deviation. So given that they're normally distributed, we can calculate the statistics for the margin of safety. The mean value of the margin of safety is just the difference in the mean value of the resistance and load, mu R minus mu Q. Then the standard deviation, or more important, I guess more correctly, the variance, the square of the standard deviation of the margin of safety, is equal to the sum of the variances of the resistance and the load. And then we have to subtract this correlation term, minus 2 rho RQ sigma R sigma Q. So there's a covariance term going on there. And the reason why we subtract it is that if the load and resistance are strongly correlated, that means that if you happen to be out here on the load, you would also happen to be out here on the resistance, right? If the load, I got those backward. If the resistance is high, then the load also tends to be high. And so that reduces the standard deviation of the difference between those two random variables. And then importantly, if we're taking the difference between two random variables, we get between two normally distributed random variables, we get a normally distributed random variable. So that's the nice thing about margin of safety, is that now we know the distribution function for the margin of safety, whereas the factor of safety would have a more complicated distribution function. So what we can do then is plot the resulting random variable m versus probability density, right? So here's the probability density function for the margin of safety. There will be a region where the load is bigger than the resistance, right? If we look up here, there is some region where the resistance is smaller than the load over there. So we're going to get something that has a smaller load and resistance, a smaller resistance than load, and that is a failure, right? If the resistance is smaller than the load, then the thing would fail. And now we can quantify a couple things as well. We've got the standard deviation and mean of the mean and standard deviation of the margin of safety, right? We can compute those up here. And then the distance between 0 and the mean is equal to beta times m. And we'll talk about this beta in just a second. Beta is a scalar. It has no units. It's the reliability index, and we'll use it to compute the probability of failure. And if we're looking at the probability density function, then the area of the probability density function that's below 0 is equal to the probability of failure. And the area that's above 0 is equal to the probability of survival, right? So they're complementary. 1 minus the probability of failure is equal to the probability of survival. Recall the property that the integral of a probability density function from minus infinity to plus infinity is equal to 1, right? Okay, alternatively, we can plot the cumulative probability density function, which is just the integral of this as you go along. And in that case, the point of crossing here of 0 is equal to the probability of failure. So that value is equal to this integral if we do the cumulative probability density function. So I talked about this beta. It's equal to mu m over sigma m, and it's equal to the reliability index. From an intuitive perspective, as beta gets bigger, right, your mean is moving further away from 0 as a function of the number of standard deviations. So it's like how many standard deviations above failure is the mean value of your margin of safety. And you want that to be a big number. As that number gets bigger and bigger, it means that, you know, you're getting a distribution that's way out here. Now, beta can get big by two different ways, right? You can increase the mean value of the margin of safety. That would be making something stronger, increasing the resistance. Decreasing the load is usually not available as an option to us, right? The load is defined by external forces that are beyond our control. But we can increase resistance sometimes, make that mean value of the margin of safety go up. Or we can reduce the standard deviation of the margin of safety. And sometimes the standard deviation arises from lack of information. We don't have enough data, and we don't think we know undrained strength very well. So as you know, from a Bayesian perspective, we assign a big standard deviation to undrained strength. We could reduce it by getting more information, right? So that's another thing you can do. You can get a more steeper distribution function, and it'll reduce beta. Okay, so then to compute the probability of failure, it's really easy. You just do 1 minus the cumulative normal distribution, the cumulative standard normal distribution function of beta, right? So this phi function is available in almost every calculation tool that you'll find. You can do it in Excel if you want to. You can do this in MATLAB, Python, whatever you want. You'll find this function in a lot of different places. And then you can also make tables. So here's a column of beta values, and here's a column of the corresponding probability of failure. If beta is negative, that means that the mean value is actually below 0, right? Your factor of safety would be less than 1 in that case. And so the probability of failure, if beta is -3, the probability of failure is 99.9%. You're almost guaranteed to fail in that case. And then as beta increases, the probability of failure goes down. At -2, it's only 0.977. Once you get to 0, it's 50-50. Right? So if you design it for a factor of safety of 1, half the time it'll fail, half the time it won't fail, as long as you've done an unbiased estimator of factor of safety. And then as you get up to like 5 for beta, the probability of failure is now 2.9 times 10 to the -7. Pretty low probability of failure, right? So one thing to note, probability of failure never becomes 0. There's always some finite risk of failure. So no matter how conservative you are in your calculation, there's some chance that the thing that you've designed will fail. And maybe it's because you estimated the strength to be too high, and there's actually a zone with lower strength. You know, it's all those uncertainties that are coming into play here. So let's do a quick example problem. This is a really simple example because it has a closed form solution. Generally, for reliability problems, there is no closed form solution. And I'll talk about ways of approximating the probability of failure at the end of this lecture. So here is the problem. We have just a vertical cut in an undrained clay condition. So, you know, as long as clay has a good undrained shear strength, you can come in and make a vertical cut without a retaining wall. And that's the case that we have here. The clay will hold itself together, at least during undrained loading. Over time, it'll drain and fail, but we'll assume that undrained loading governs here. So in this case, the failure surface is inclined at 45 degrees since phi is equal to 0, and we only have 3 forces acting on the failure wedge. Vertical load is the weight, then we have a normal force and a shear force acting on the failure surface. And here I've set some properties, right? The mean value of the unit weight is 16 kilonewtons per meter cubed. The standard deviation of unit weight is 1.5 kilonewtons per meter cubed. And then the mean undrained strength is 40 kPa and the standard deviation is 10 kPa. So more uncertainty in undrained strength here than in unit weight, which is common, right? A common way of quantifying this is the coefficient of variation, which would be the standard deviation divided by the mean for each parameter. So 1.5 over 16 is smaller than 10 over 40, right? This would be the coefficient of variation for undrained strength would be a 0.25, 1/4, which is kind of in the range of reasonableness. Okay, and then we're going to assume that there's some correlation between unit weight and undrained strength, and it's fairly high, 0.7. The correlation has to be between -1 and 1. 0.7 is a pretty strong correlation, right? That means that if the unit weight is on the upper end of the range of the distribution, then the strength is also going to probably be on the upper end of that distribution. So we have to do the physics here. We have to calculate margin of safety, which means we have to calculate the load and the resistance. And what I'm going to use is the shear stress, the equilibrium shear stress acting on this plane as the load, and the undrained strength as the resistance. So we don't have to do calculations to get the resistance. We already have it here, right? The load, we do have to do some calculations because we have a random variable for unit weight, and we have to do the physics by statics to get it. So I'm solving for sum of forces in the y direction, that's vertical, and you end up with this equation. Then we have sum of forces in the x direction, and that tells us that t has to be equal to n, and then you plug in t equals n up here, and you can get t is equal to w over root 2. Now, we have to remember some things about normal distribution functions. So the weight of the slice is equal to the unit weight times the area. The area is 1/2 h squared, so the weight is 1/2 gamma h squared. But gamma is now a random variable. It's not a constant. We're used to operating on constants. So we have to figure out now what's the distribution function for the weight of the slice. Well, if you multiply a normally distributed random variable by a constant, you get a normally distributed random variable that's just scaled by that amount, right? So the mean value of the weight is 1/2 times the mean value of the unit weight times h squared. And similarly, the standard deviation scales by the same constant as well. So you had a distribution for unit weight, now you have a distribution for weight. The units are different on those things, but we know how to calculate the mean and standard deviation, and it remains normally distributed. Okay, and then we have the length of the failure surface here, right? So what we need to do is calculate big T divided by L, and that's equal to the shear stress. So we have the mean value of shear stress is the mean value of this big T parameter divided by L, so it's mu W divided by root 2 L. And again, we're just scaling things by constant numbers, so the mean value of tau can just be computed based on the mean values of unit weight and so forth. And then the standard deviation of tau also scales. So we end up with the mean value of tau is 16 kPa, and the sigma on tau is 1.5 kPa. So now we have our margin of safety. It's equal to SU minus tau. The mean value of the margin of safety is equal to the difference in the means of SU and tau. So it's 40 minus 16 kPa. We get 24 kPa. Then the standard deviation of the margin of safety can be computed from this equation in terms of variances. So I'm plugging in numbers here, here, there, and then taking the square root, and we get the mean value of the margin of safety is 9.01 kPa. Okay. Then the beta is mu m over sigma m, and I get 2.663 for beta. So in this case, we're 2.663 standard deviations away from failure. And the probability of failure is 3.88 times 10 to the minus 3. So, you know, if you designed 1,000 of these, 3.9 of them would fail on average. Okay, so one thing is that we assume this correlation between unit weight and undrained strength. And they're correlated because, as I mentioned, denser soil is also stronger. So they should be correlated. But what if we ignored that? What if we just assumed that the correlation was 0, that unit weight and undrained strength were completely uncorrelated from each other? Well, what that means is that now there's more of a chance of getting a high unit weight combined with a low undrained strength. And so our probability of failure should go up, right? Because we're taking away that correlation. So the mean value of margin of safety stays the same, but the standard deviation of margin of safety does indeed go up. And you can see it goes up because we're subtracting, right here, we're subtracting a number that was bigger and now it's 0, right? So if we set that to 0, we're not subtracting that. So the margin of safety should go up. Okay, so then we get beta is equal to only 2.373 instead of 2.663, so it went down a little bit. And the probability of failure is now 8.8 times 10 to the minus 3. All right, so whereas we had 3.9 times 10 to the minus 3 before. So probability of failure did indeed go up. Now, you might be asking, what is a suitable probability of failure, right? We've already said, like, we know sometimes we have to design for a specific factor of safety. Now we know how to compute probability of failure, but how do we know what probability of failure to design for? That's a problem, right? That's a hard problem. It depends a lot on consequences. If you're designing an earth dam that, if it fails, would flood and kill a lot of people, you better design for a low probability of failure. If you're designing the foundation for a shed and failure doesn't really matter very much, you might be willing to accept a little more risk and go with the higher probability of failure. Your design can be cheaper that way. So that's where engineering judgment comes into play, maybe negotiations with clients and so forth. All right, now this example problem that we did on the vertical cut had a closed form solution, which makes it really nice to illustrate some key concepts, but it's not particularly realistic. The reason we could do a closed form solution is that tau was a linear function of gamma, right? All that we did was multiplied a random variable by some constants in order to get the equilibrium shear stress distribution. Therefore, we could compute them directly. In general, the physics of the problem are more complicated, and it's almost never the case that we can get a closed form reliability solution, a closed form expression for probability of failure. So we have to use numerical methods to find the probability of failure. And this is what slide does in the method of slices, right? A good example of why this is a closed form solution is not usually possible. You can imagine running slide analyses where the strength of the soil and the unit weight were random variables. Well, as the strength changes and the unit weight changes, the critical failure surface is going to change too, right? In this problem, we knew that the critical failure surface was inclined at a 45-degree angle. If that now is starting to become a function of the soil strength, it makes the problem more complicated, and there's just not going to be a closed form solution anymore. So in slide, what it does is something called Monte Carlo simulation. And Monte Carlo simulation is kind of a brute force way of approximating the probability of failure. It sounds fancy, like we're gambling or something. It's actually not super fancy or complicated. The concept is really simple. What you do is generate a large number of realizations of your random variables. In this case, we would generate a large number of realizations for unit weight and undrained strength, since those are our two random variables. Then for each realization, we calculate the margin of safety, right? The difference between the capacity and the demand. And what we want to know is what percentage of those realizations results in failure. So we have to do the summation over the failed cases, right? So F for failure is equal to 1 if the margin of safety is less than 0, and it's equal to 0 if the margin of safety is bigger than 0. So if we were to randomly generate 1,000 realizations of the problem that we've just solved, we would expect about 9 out of those 1,000 to fail if we had no correlation. If we include correlation, we would expect about 4 out of 1,000 to fail. So you can see the smaller that this number gets, the more realizations you're going to have to do. If this probability of failure was like 10 to the minus 7, probably all 1,000 realizations would not fail, right? And you would approximate a probability of failure of 0. So there's limitations to Monte Carlo simulation. If you really want high reliability, you're going to have to do a really large number of simulations. So let me just show you real quickly for this problem an example calculation that uses Monte Carlo simulation. So this is a Jupyter notebook. I'm using a Python code here to illustrate the concept. And so we're solving we're using Monte Carlo simulation to solve the same problem that we've had before. Except I'm going to solve it for the correlation coefficient equal to 0. The reason I'm doing that is that it's really easy for me to generate random numbers that are uncorrelated with each other. If we were to try and generate correlated random variables, it becomes a little more complicated. You can do it. It's definitely possible using a process called Cholesky decomposition, so you can convert uncorrelated random variables into correlated random variables, but I felt like that was a little too far just to illustrate the concept. So anyway, we've got these inputs. Here's the f parameter, and then here's my code. And let me walk you through the steps here in the code. So what I'm doing, this first statement is an import statement, import numpy as np. So this is a Python package that allows you to do calculations, and within that package it has a random number generator. So I can do a normal distribution function and generate a bunch of random numbers using numpy. Then this set of, 6 lines, 7 lines, I'm defining the input parameters. So we have the mean value of the unit weight is 16. The standard deviation of the unit weight is 1.5. The mean value of the undrained strength is 40. The standard deviation is 10. Then I'm doing 100,000 Monte Carlo simulations. So n is 100,000 here. The height is 4 meters, and then the length of the failure surface is 2h over square root of 2. I think that's like 5.7 meters, something like that. All right, now in lines 11 and 12, this is where I'm generating the random numbers. So numpy has this random.normal function. This is the mean value and the standard deviation, and then the number of random numbers that I want drawn from that distribution function. Same thing for undrained strength. So now we have two uncorrelated vectors of realizations of these random variables, gamma and SU. Now what I'm doing in this code is computing the probability of failure. So I'm setting it to 0 initially. And then I don't know how many of you have used Python before, but it has this really kind of cool way of doing for loops. So instead of just putting an index counter and referencing, some row in a list or a column vector or an array, you can put, in this case, for g comma s in zip gamma comma su, and every time it iterates, g will be the corresponding value of gamma. So it'll start with the first value, go to the second one, third one, and so forth. And I don't have to worry about indexing. I can just use this variable g inside my loop for gamma and s for undrained strength. So here's the weight of each realization, right? Note that gamma is going to be different every time, so we have to calculate the weight for each realization. Here's the equilibrium shear stress. This is the margin of safety. It's equal to the undrained strength value minus tau. And then I'm not actually computing that f variable that I put in the equation up here, but what I'm doing is if the margin of safety is less than 0, I'm adding 1 over n to the probability of failure, where n is the total number of loops that we have. And then you can do print probability of failure equals this, string of the probability of failure value. So let me run this. Run. Okay, it took a little bit of time, but I got a probability of failure of 0.00866. It agrees pretty well with the closed form solution. And if we run it again, we'll get a different number, right? Because now we get 0.865. Also, if we reduce the number of simulations, let me go to 1,000. Now we're going to get more variability in the probability of failure. It's a less stable predictor. The more simulations you do, the more accurate you're getting the probability of failure. So we're overestimating it now in this case. But anyway, that's how Monte Carlo simulation works, and that's how SLIDE does the reliability calculations for slope stability problems.